Before moving on to some other shapes in kind of polar and Cartesian graphs, we're going to look at one other example of a line. Here's a line that I've drawn through the polar graph, but I don't have its equation. And so one thing we're going to do here is try to figure out its equation and then see if we can convert it to a Cartesian form. So let's kind of take a look at what this would be like on Desmos first of all. So here I've kind of got my secant equation, and so I'm going to try and rotate it, and I'm going to, I guess I can kind of rotate the line around and get it kind of looking like my graph paper. So maybe it's something like that. This is just kind of estimating it right here, and then let's kind of see going. Okay, that looks kind of, looks pretty good. But then I realize I've got to take the normal and bring the normal down. So I need to shrink the normal down. So I'm going, okay, smaller, 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 and so I get really close. But then when I say, well, there is no normal, I kind of lose the line, and then kind of pick it back up again. You'll notice then going, so this form, this secant form, is really good for almost every line you could think of, except the line where you try to pass through the origin. You'll notice that in that particular case, you really don't have a normal, and this format really relies on a normal. So we're going to have to totally abandon this secant, cosecant form. Clearly, you can draw it, so you're figuring there's got to be an equation for it. And how can we figure out the equation? Well, it probably, you go back to the beginning or the basics of like, well, how do we get equations? Equations represent relationships. In this case, relationship between r and theta. So we're going to look at a few points and we're going to see what we notice. So for example, in this picture here, if I go out 1 unit and then I rotate 30 degrees, I've got that point right there. So that would be 1, 30 degrees. If I were to go out 2 units and rotate 30 degrees to 30, and you start to realize, hey, wait a minute, it's always going to be like 30 degrees. In fact, even if you pick a negative number like -2, rotate 30 degrees. You start to realize, okay, r could be pretty much anything we want, but what remains constant is the rotation of 30 degrees. This is a constant equation. In this case, it's the theta, okay, that's held constant at 30 degrees. Okay, theta equals 30, and that would be an equation that represents what we see in this picture. Theta equals 30. Now it turns out, again, it's very typical in polar, there are multiple ways to describe things. Someone could say, well, wait a minute, I'm looking at it as if I go out 3 and I rotate -150 degrees. Or if I go out 2 and rotate -150 degrees. If I go -3 and then rotate -150 degrees, that would work as well. 0 equals -150. Other students will say, well, hang on, there's more than that. If we go out 4, we could rotate 210 degrees, okay, and we could get to that spot. So there's another option. Okay? In fact, there's an infinite number of equations that would make this red line. So let's kind of just take this one right here, this version, probably the simplest of them, and ask, okay, can we now convert this to Cartesian form? In other words, express it in terms of x and y. And unfortunately, like in the previous videos where I was kind of using the intercept method, I only have one intercept here. The intercept is at 0. I really don't have an x and a y intercept. So it's kind of hard to kind of set up right triangles and do some trigonometry. So, well, let's think about what we can do. If we were to say go out 3 units, okay, and then we would go up a certain amount, okay, that would be the Cartesian value. So for each x, I go up a certain amount of y. And so let's kind of put 3 right here. And then is there a way to find out what this value is right here? Let's call this y for right now. Is there a way to do this? And you think, well, yeah, this is a 30-degree angle right here. And so I could say tangent of 30 equals y over 3. So I can say tan 30 equals y over 3. Now, some of you may remember in a 30, 60, 90, there's a special relationship in the sides. But let's just say, either you've forgotten that or you'd rather just kind of do a little more quickly on your calculator. So we'll go tan 30, and then we're going to multiply that by 0.3, or multiply that by 3 times 3 equals about a 1.732 equal to the y. Now that's not the equation of the line, mind you. That's just going to be this distance right here. So I'll cross that out and put 1.732. But notice what you have is you now have rise and run. You have rise and run. So you can now start to design an equation. Y equals, rises 1.732 and runs 3 units. And then the intercept is a 0. So if you want to clean that up a little bit, you end up with y equals, let's see, 1.732 divided by 3, 0.577 x. And that equation would be the slope of the line. So it's pretty easy to change. Now, if you just want to do this purely from an algebraic standpoint, and again, you may have to think a little bit about this. Here was your original. And you might recall where that 577 came from. That was the tangent of 30 degrees. So really, if you just kind of said, oh, let's just take the tangent of both sides, tan theta equals tan 30. This would be your 577. But then what's this tan theta thing? Well, again, let's kind of go back and think about the relationship between Cartesian values, x and y, and then polar values, r and theta. Okay? Tangent of theta is simply y over x. So this is y over x equals 5.7. And now if you multiply the x over to the other side, you get y equals 0.577x. So it's actually very simple. You just take the tangent of both sides, and then that all turns your equation into a Cartesian value right there. So, not too bad. So even when lines go through the origin, okay, or the pole, you can't really turn them into secant or cosecant equations, but you'd have to go with sort of a straight theta equals number. It's a constant function. Theta is held constantly at something. So now let's say we had to go the other way. Let's say we've got something that's already in Cartesian. Can we draw it and then convert it over to polar? So drawing is actually pretty easy. You've got rise 2, run 1. So from origin up 2 over 1, up 2 over 1, or down 2, back 1, down 2, back 1. So here's your your line. And really what we're trying to figure out is, okay, this is theta equals something. Let's see what we can do here. Well, here's our angle theta right here. That's what we really need to figure out. And again, we can create a triangle. So I'll go with, say, 2 and 4. When x is 2, y has to be 4. And so now I could do tangent of theta equals 4 over 2. Tan theta, 4 over 2. And we could then do a little inverse tangent of 4 over 2. So let's say second tangent of 4 divided by 2. And we get about 63.43 degrees. 63.4, which looks pretty good. That looks like it's pitched at about a 63.43 degree angle. And so that, again, is fairly simple. Now, of course, we could also look at the, say, 63, let's add on 180 degrees. We could also say 243.43 degrees. Or perhaps we could find a negative rotation. Theta equals negative, 116 point something. So lots of options there. Now, if you wanted to do this without the aid of a graph, in other words, could you do it from a purely algebraic standpoint? The answer is yes. And so we would start with our equation. And then we'd want to try and set up a ratio of y over x. So if we divide the x over, we have y over x equals 2. And then we say, well, okay, well, y over x, again, thinking about that little triangle, y over x is the same as tan theta. So we have tan theta equal to 2. And now we could take the inverse tangent of 2. And that would be, again, 63.43 degrees. And that's kind of doing it sort of a purely algebraic fashion, just making some substitutions. So lines that go through the pole or the origin are really not very difficult at all. You just have to kind of step away from the, trying to make it a secant or cosecant equation. You can't really use kind of two intercepts because there aren't two intercepts. There's only one intercept, namely the origin. So that's going to wrap it up for lines. On the next videos, we'll look at some of the other more complicated shapes like circles and hyperbolas and ellipses. Thanks for watching.